Hello there, and welcome to Deep Sleep Seas. I'm so glad you found your way here tonight. Maybe you've had a long day, or perhaps you're the kind of person who finds comfort in drifting off to the sound of oceanic mysteries and the quiet wonders hidden in Earth's most remote places. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened its hold. Because tonight we're traveling to one of the most extraordinary and least explored environments on our planet. We're venturing beneath the great floating platforms of ice that ring Antarctica like frozen buttresses against the sea. These are the ice shelves, quiet kingdoms beneath the ice where darkness reigns eternal and life persists against all odds. These immense shelves of ice, some as large as entire countries, float upon Antarctic waters in near total silence. They are neither quite glacier nor quite sea ice, but something altogether different, structures of such scale and age that they dwarf human history. Beneath them lies an ocean world that has only recently begun to reveal its secrets, a world of slow currents and ancient creatures, of water pressed between ice and stone, of darkness so complete that the very concept of light becomes abstract. Some of what you hear tonight may surprise you, or at the very least spark some curiosity as you drift off to sleep. But before we begin, if you find these stories relaxing, consider subscribing so you don't miss the next deep-sea journey. And if you're awake enough, let me know where in the world you're listening from. I read every one. Now, let's begin. Imagine standing at the edge of the world. Not metaphorically, but literally at the point where solid land gives way to an ocean frozen at its surface, where the boundary between continent and sea blurs into something vast and strange. This is where ice shelves begin. They are massive platforms of glacial ice that have flowed from the land out over the ocean, floating atop the water like colossal rafts, yet remaining connected to the glaciers that feed them. Unlike sea ice, which forms each winter from frozen ocean water and melts each summer, ice shelves are permanent structures that can persist for thousands of years. Unlike glaciers which rest upon bedrock, ice shelves drift upon the sea, held in place only by their connection to land and by friction with the islands and peninsulas that surround them. The ice shelves of Antarctica cover more than 1.5 million square kilometers of ocean. That's an area larger than the entire nation of Mongolia. Larger than Peru, nearly twice the size of Turkey, and yet for all their vastness, they remain among Earth's least known environments. Most of us will never see them except in satellite images, never feel the profound cold that grips them, never witness the slow dance of their movement as they flex with the tides and creep gradually seaward. They exist in a realm so remote, so inhospitable, that they were among the last places on Earth to be properly explored. Even now, decades after humans first set foot on the moon, we know more about some distant planetary surfaces than we do about what lies beneath these frozen platforms. The story of ice shelves begins not at the coast but far inland, high on the Antarctic ice sheet where snow falls year after year, century after century, millennium after millennium. This snow accumulates into layers, each winter's deposit adding to the one before, pressing down with ever-increasing weight. Under this tremendous pressure, the snow transforms. Air is squeezed from between the crystals. The delicate, branching structures of snowflakes collapse and merge. Over decades and centuries, the snow becomes firn, a dense granular substance, halfway between snow and ice. With more time and more pressure, the firn becomes true glacial ice, blue and clear and ancient. This ice does not simply sit still. Under its own immense weight, it begins to flow. Like honey poured onto a table, like wax dripping down the side of a candle, the ice moves. It flows downhill following the subtle contours of the bedrock buried beneath, channeled by valleys and ridges, accelerating where the slope steepens. In some places, the ice flows at just a few meters per year, a pace so glacial that the word itself has become synonymous with slowness. In other places, in the great ice streams that drain the interior, the ice surges forward at hundreds or even thousands of meters per year, a raging river of frozen water moving toward the sea. When this flowing ice reaches the coast, something remarkable happens. The ice is so thick, in some places more than a kilometer thick, that it doesn't simply calve off into icebergs. Instead, it keeps flowing out over the ocean, floating upon the seawater that is just slightly denser than the ice itself. The transition point where the ice lifts off from the bedrock and begins to float is called the grounding line, and it marks the beginning of the ice shelf proper. From this point forward, the ice is afloat, a platform of frozen fresh water drifting upon the salt sea. But the ice shelf is not disconnected from the land. It remains attached at its sides, held in embayments between rocky peninsulas, anchored by islands that rise from the seafloor. These pinning points, as scientists call them, are crucial. They provide friction that resists the ice shelf's forward motion, creating what is essentially a dam that holds back the glaciers behind. Remove an ice shelf, and the glaciers that feed it can accelerate dramatically, pouring ice into the ocean at many times their former rate. This is one reason ice shelves matter so profoundly. They are stabilizers, buttresses, brakes upon the great ice sheets of Antarctica. Their presence or absence can determine how quickly ice flows from land into sea, and thus how quickly global sea levels rise. The largest of these frozen platforms is the Ross Ice Shelf, named for the British explorer James Clark Ross, who first encountered its towering front wall in January of 1841. Ross and his crew, sailing aboard the Erebus and Terror, had been making their way southward through the pack ice when they suddenly found their passage blocked by what Ross described as a perpendicular cliff of ice. They sailed along this ice wall for days, following it eastward, unable to find a way through, unable even to comprehend its true scale. What they had discovered was the edge of a floating ice platform, roughly the size of France, about 500,000 square kilometers of ice, several hundred meters thick. The Ross Ice Shelf extends far into the Ross Sea, a deep embayment in the Antarctic coastline. In places it stretches more than 800 kilometers from the grounding line to its seaward edge. The ice front, the vertical cliff where the shelf meets open water, runs for more than 600 kilometers, a wall of ice rising 15 to 50 meters above the water's surface. But this visible portion represents only a fraction of the shelf's thickness, like an iceberg. Most of the ice shelf lies below the waterline. The ice can be as much as 750 meters thick in the south, where it is fed by massive glaciers flowing from the East Antarctic ice sheet, and it thins gradually toward the north, tapering to perhaps 100 meters near the ice front, where the oldest ice finally breaks away as icebergs. Standing on the surface of the Ross Ice Shelf, which a number of Antarctic bases and field camps do, you would see nothing but a vast flat expanse of white extending to the horizon in all directions. It would appear utterly still, utterly unchanging. A frozen desert where nothing moves and nothing happens. But this stillness is an illusion. The ice shelf is constantly in motion, flowing northward at speeds ranging from 1.5 to 3 meters per day. That's roughly a kilometer per year, fast enough that if you left equipment on the surface and returned a decade later, it might be 10 kilometers from where you left it, carried along by the inexorable forward motion of the ice. And the Ross Ice Shelf is not alone. Its sister platform, the Filchner-Ronne Ice Shelf, lies on the opposite side of the continent in the Weddell Sea. This shelf is even more massive in some ways, though it covers a slightly smaller area, about 430,000 square kilometers. The Filchner-Ronne is actually two connected shelves that are only partially separated by Berkner Island, which rises from the seafloor to pierce the ice. The ice here is extraordinarily thick in places, approaching 2,000 meters at the grounding line, nearly 1.25 miles of solid ice floating upon the sea. The water beneath, in the deepest parts of the cavity, can be 1,400 meters deep. Imagine that, a gulf of seawater almost 1 mile deep, trapped between ice above and seafloor below, a hidden ocean existing in total darkness beneath one of the thickest ice platforms on Earth. These two shelves, the Ross and the Filchner-Ronne, together account for the majority of Antarctica's ice shelf area. But they are far from the only such structures. All around the Antarctic coastline, wherever glaciers flow down to the sea and where the geometry of the coast provides even a small amount of protection from the open ocean, ice shelves form. There's the Imagery Ice Shelf in East Antarctica, fed by the massive Lambert Glacier. There's the Larsen Ice Shelf complex on the Antarctic Peninsula, or what remains of it after dramatic collapses in recent decades. There are dozens of smaller shelves, each one a unique system with its own glaciers, its own ocean cavity, its own particular balance of growth and loss. The Arctic has ice shelves too, though they are far less extensive than their Antarctic cousins. Along the northern coast of Ellesmere Island in the Canadian Arctic, thick platforms of ice once extended far out to sea. These Arctic shelves are different in character from Antarctic ones. They form not only from glaciers flowing off the land, but also from sea ice that has persisted for so many years that it thickened and consolidated into something more permanent, something almost shelf-like. But the Arctic is warmer than Antarctica, and its ice shelves are smaller, more vulnerable, more transient. Many of the Arctic shelves that existed a century ago have now broken up and disappeared entirely, their remnants drifting as ice islands in the Arctic Ocean. In Greenland, outlet glaciers from the ice sheet sometimes extend far enough to float, creating small ice tongues and protoshelves, but the warmer waters and more vigorous ocean circulation typically break these up before they can develop into true ice shelves. It is Antarctica, cold, isolated, surrounded by the circular flow of the Antarctic circumpolar current, where ice shelves reach their fullest expression, where they achieve scales that dwarf anything the Northern Hemisphere can produce. To understand what makes ice shelves so remarkable, you have to understand what lies beneath them. Imagine drilling down through hundreds of meters of ice, through the accumulated snowfall of thousands of years, through blue glacial ice that has flowed from far inland. Your drill finally breaks through into open water. You lower a camera into the hole, expecting to see nothing but darkness and perhaps a few fragments of ice. Instead, you discover an entire hidden ocean. This is the sub-ice shelf cavity, and it is one of the planet's most extraordinary and least accessible environments. The cavity exists because ice shelves float. The ice is just slightly less dense than the seawater it rests upon, and so it displaces a volume of water equal to most of its mass. The ice shelf sits with about 10 to 15% of its thickness above the water surface and the rest below. In the case of a thick ice shelf like the Filchner Ronne, this creates an enormous space beneath the ice, a cavity that can be hundreds of kilometers wide and hundreds of meters deep. This is not a still, stagnant place. Water circulates through these cavities, driven by complex interactions between tides, ocean currents, the rotation of the Earth, and the ice shelf itself. The water in these cavities is extraordinarily cold, often below the normal freezing point of seawater. It can remain liquid at -2 degrees Celsius because of its salt content. The salt depresses the freezing point, allowing the water to stay liquid at temperatures that would freeze fresh water solid. But this water is right at the edge of freezing, teetering on the boundary between liquid and solid, and the slightest change in temperature or salinity can cause ice to form or melt. When relatively warm water from the deep ocean manages to intrude onto the continental shelf and reach the underside of an ice shelf, it brings heat with it. This water might be only a few degrees above freezing, perhaps 2 or 3 degrees Celsius, but in the context of ice that is at -20 or 30 degrees Celsius internally, this is tropical warmth. The warm water melts the base of the ice shelf, thinning it from below in a process called basal melting. As the ice melts, it adds fresh, cold meltwater to the cavity. This meltwater is less dense than the surrounding seawater, and so it rises, flowing up along the underside of the ice shelf like an upside-down river, gradually making its way toward the ice front where it can escape into the open ocean. But something remarkable happens as this meltwater rises. As it flows along the underside of the ice, moving from areas of thick ice near the grounding line to areas of thinner ice near the front, the pressure decreases. Ice has a peculiar property where its melting point changes with pressure. At high pressure, deep beneath a thick ice shelf, the melting point is slightly lower. As pressure decreases toward the ice front, the melting point rises. The meltwater, having been in equilibrium with ice at high pressure, suddenly finds itself too cold for the lower pressure environment. It's now below the local freezing point, and so it does something unexpected. It freezes. New ice forms on the underside of the ice shelf, not from the compaction of snow above, but from the freezing of seawater below. This is called marine ice, and it can accumulate in layers hundreds of meters thick. Scientists have drilled through ice shelves and found these layers, ice with different crystal structures, different chemical signatures, ice that contains trapped seawater and has a higher salt content than the meteoric ice that formed from snow. The largest body of marine ice yet discovered lies beneath the central portions of the Filchner Ronne ice shelf, a layer that in some places reaches 300 meters thick, accounting for more than half the total thickness of the ice shelf in those areas. The circulation of water beneath ice shelves is complex and three-dimensional. Cold, dense water sinks. Warm, less dense water rises. The Coriolis effect, caused by Earth's rotation, deflects moving water to the left in the southern hemisphere, creating spiraling currents. Friction between the water and both the underside of the ice and the seafloor generates turbulence that mixes water masses and enhances heat transfer. The tides, the regular rise and fall of sea level caused by the gravitational pull of the moon and sun force water to slosh back and forth beneath ice shelves, creating currents that can reach tens of centimeters per second during spring tides. These tidal currents are crucial. They stir the water, preventing stratification, bringing warmer water into contact with the ice base where it can drive melting. The tides also cause the ice shelf itself to flex and bend. Twice a day, as the tide rises and falls, the entire ice shelf lifts and drops by several meters. Where the shelf is pinned to islands or to the bedrock at the grounding line, this vertical motion creates bending stresses that can propagate cracks and rifts through the ice. In some places, the tidal motion is so pronounced that it modulates the flow of the glaciers themselves. Scientists have measured glaciers that speed up and slow down with the tides, flowing faster during low tide when the ice shelf drops and pulls forward on the grounded ice, and slower during high tide when the shelf rises and pushes back. This interplay between ice and ocean, between floating shelf and flowing glacier, between tidal forces and long-term circulation, creates a dynamic system that is only now beginning to be understood. For decades, ice shelves were thought of as relatively simple structures, static platforms that merely sat there accumulating ice from above and losing it to calving at the front. But detailed measurements and sophisticated modeling have revealed them to be far more active, far more sensitive to their environment than anyone suspected. They flex with the tides, they thin and thicken in response to ocean temperature, they crack and rift and heal. They are, in a very real sense, alive. And they are not empty. For the longest time, scientists assumed that the water beneath ice shelves was essentially sterile, too cold, too dark, too isolated to support life. Sunlight cannot penetrate hundreds of meters of ice. Photosynthesis is impossible. Without photosynthesis, without the base of the food chain that supports nearly all life on Earth's surface, how could anything survive? The expectation was that these sub-ice cavities might harbor a few hardy bacteria, perhaps some microscopic organisms eking out an existence on geothermal heat or chemical energy, but nothing more. This assumption began to crumble on a summer day in February 2021, when a team of geologists drilling through the Filchner-Rhone ice shelf had an unexpected encounter. They were 900 meters beneath the ice surface, 260 kilometers from the open ocean, trying to collect sediment samples from the seafloor. The water temperature was -2.2 degrees Celsius. No sunlight had touched this place in thousands of years, perhaps tens of thousands. When they lowered their video camera through the borehole, expecting to film the drill striking soft sediment, they instead watched it hit a boulder. The rock itself was unexpected, solid bedrock in what should have been a muddy seafloor. But what they saw on the rock was even more surprising. The boulder was covered in life. Attached to its surface were what appeared to be sponges. Lots of them, along with other organisms that were harder to identify from video alone. There were stalked creatures that might have been barnacles or hydroids, relatives of jellyfish. There were blob-like masses that were certainly some kind of sponge. There were possibly tube worms and other filter-feeding organisms, all of them stationary, all of them anchored to the rock, all of them thriving in conditions that by all conventional wisdom should have been completely inhospitable to life. Filter-feeding organisms depend on a supply of food from above. They sit in one place and strain organic particles from the water, tiny fragments of dead plants and animals, fecal matter, the constant rain of organic debris that falls through the ocean in places where sunlight drives photosynthesis. But here, beneath hundreds of meters of ice and hundreds of kilometers from the nearest light, there should be no such rain of food. These organisms should starve, and yet, they were not just surviving. Based on their size, they had been growing here for years, possibly decades, possibly much longer. How do they eat? The scientists still don't know for certain. The most likely explanation involves the ocean currents that flow beneath the ice shelf. These currents originate far away, in regions of open water where photosynthesis does occur, where algae bloom and tiny zooplankton graze and the usual marine ecosystem operates. As the water flows beneath the ice shelf, it carries with it organic matter, nutrients, the chemical and biological wealth of the surface ocean. The journey might be hundreds of kilometers long, the flow might take months or even years, but the delivery continues. The organisms on that boulder, and presumably on other boulders and rocky outcrops scattered across the sub-ice seafloor, live off this slow subsidy of food transported from distant sunlit waters. Carbon dating of dead fragments collected from a similar community told an even more remarkable story. Some of the organic material was recent, formed within the last few years or decades, but other fragments dated back thousands of years. One piece of dead sponge was 5,800 years old. This suggests that communities like this have existed beneath Antarctic ice shelves not just for years or decades, but for millennia. These are ancient ecosystems, established long before recorded human history, persisting through centuries and millennia in the darkness, slowly growing, slowly filtering the passing water, unaware of and unaffected by the rise and fall of civilizations in the sunlit world above. The discovery sparked a renewed interest in exploring beneath ice shelves. Scientists realized that they had been systematically underestimating the biodiversity of these environments. Prior expeditions had found evidence of mobile life, fish that swam through the cavities, jellyfish drifting with the currents, amphipods scurrying across the seafloor. These mobile animals made sense. They could travel to find food, could move between the ice shelf environment and the open ocean, could forage and hunt in ways that allowed them to survive, despite the absence of local photosynthesis. But the presence of abundant sessile organisms attached to the seafloor suggested something more. It suggested that the sub-ice environment was productive enough to support not just a few scattered survivors, but entire communities. In January of 2025, another discovery made headlines. A massive iceberg, roughly the size of the city of Chicago, carved from the George VI ice shelf in the Bellingshausen Sea off the Antarctic Peninsula. The iceberg, designated A84, drifted away from the coast, leaving behind a newly exposed section of seafloor that had been covered by ice for centuries. An international team aboard the research vessel Falkor rapidly changed their research plans and sent a remotely operated vehicle down to explore this freshly uncovered seabed. What they found was astonishing. The seafloor was not barren. It was, in the words of one scientist, beautiful and thriving. Large sponges dotted the landscape, some of them more than a meter across. These sponges grow extremely slowly, sometimes less than 2 centimeters per year, which meant the specimens they were seeing could be decades or even centuries old. Clusters of sea anemones swayed gently in the current. Corals, including deep-sea corals that normally live in open water but somehow had colonized this recently ice-covered region, created structures that hosted a remarkable diversity of other animals. Icefish swam through the water, their blood containing antifreeze proteins that allowed them to survive in the frigid temperatures. Giant sea spiders, arthropods with leg spans that could exceed half a meter, crawled across the seafloor on delicate, multi-jointed limbs. Octopuses rested in crevices, their intelligent eyes watching the submersible's lights. A giant phantom jelly, a species of jellyfish that can grow up to a meter wide with ribbon-like oral arms stretching more than 10 meters long, drifted through the water column like a pale ghost. Brittle stars climbed on sponges. Solitary hydroids swayed in the current. Squid hunted fish. An entire ecosystem, vibrant and complex, existed in a place that had been sealed beneath ice until just weeks before. The scientists hypothesized that ocean currents must be the key to sustaining this life. The currents carry nutrients, oxygen, and organic matter from productive waters elsewhere. The ecosystem is not locally self-sustaining through photosynthesis, but it is sustained by the ocean's circulatory system, by the great rivers of water that flow around Antarctica and penetrate beneath its ice shelves. This hypothesis is supported by the fact that different species are found at different distances from the ice front. Near the edge, where currents are stronger and the connection to the open ocean is more direct, diversity and abundance are higher. Farther from the edge, deeper beneath the ice where currents weaken and food delivery becomes more sporadic, life becomes sparser, though it never entirely disappears. These discoveries have profound implications. They reveal that ice shelves are not biological deserts, but are instead ecosystems in their own right, communities adapted to life at the edge of survival, thriving in one of Earth's harshest environments. They also raise urgent conservation questions. If ice shelves collapse due to climate change, these ecosystems will be exposed to light, to warmer water, to entirely different conditions. Some species might adapt, others will certainly perish. Unique communities that have existed for thousands of years could be lost in a matter of decades or even years. And once they are gone, once the particular conditions that allowed them to form are destroyed, they can never be recreated. The study of life beneath ice shelves is also revealing broader truths about biology and evolution. It demonstrates that life is extraordinarily resilient, but it can find a way to persist in almost any environment where liquid water exists and where some source of chemical energy or nutrients can be found. It shows that ecosystems do not have to be based on local photosynthesis. They can import their energy from elsewhere, can survive on a trickle of food delivered by currents over hundreds of kilometers. This has implications for the search for life elsewhere in the solar system. Jupiter's moon Europa and Saturn's moon Enceladus both have liquid oceans beneath thick ice shelves. If life can exist beneath Antarctic ice shelves, sustained by currents and distant food sources, perhaps it could exist beneath the ice of these distant moons as well. But ice shelves are not just habitats. They are also dynamic structures, constantly changing, constantly responding to the forces that act upon them. They grow as glaciers feed them ice from behind, and as snow accumulates on their surfaces. They grow from below as marine ice accretes, and they shrink as icebergs calve from their fronts and as melting removes ice from their bases. In a stable climate, these processes of growth and loss balance, and the ice shelf maintains a roughly constant size and thickness. But climate is not stable, and ice shelves are exquisitely sensitive to changes in both the atmosphere above and the ocean below. The atmosphere affects ice shelves primarily through temperature. When air temperatures rise above freezing during the summer, the snow on the ice shelf surface can begin to melt. Meltwater pools on the surface, forming shallow ponds of liquid water that darken the ice and absorb more sunlight, which drives further melting in a feedback loop. If these melt ponds are extensive enough and persistent enough, they can cause problems. The water seeps into cracks in the ice, into the crevasses that naturally form in any floating ice shelf as it flexes and stretches. Water is much heavier than air, and when a crevasse fills with water, the weight of that water can deepen the crack, can drive it further into the ice, can even propagate it all the way through the ice shelf in a process called hydrofracture. This process of surface melting and hydrofracture is thought to be a major contributor to ice shelf collapse. It creates a situation where the ice shelf is riddled with water-filled cracks, weakening its structure, making it vulnerable to breaking apart. Once enough cracks form, once the ice shelf has been sufficiently weakened, it can disintegrate rapidly, sometimes in a matter of days or weeks, breaking into thousands of small icebergs that drift away and melt. The most dramatic example of this process occurred on the Antarctic Peninsula in early 2002. The Larsen B ice shelf, a platform of ice covering more than 3,000 square kilometers, roughly 1,200 square miles, an area about the size of Rhode Island, disintegrated in just over a month. Satellite images captured the event in stunning detail. At the start of the summer, the ice shelf was intact, though its surface was pockmarked with blue melt ponds. The ponds were arranged in parallel lines, following the crevasses that naturally formed in the ice. Over the following weeks, the shelf began to break up. Long fingers of open water appeared, extending inland from the ice front. Sections of the shelf broke away as tabular icebergs, and then with shocking speed, the entire remaining shelf shattered. Where there had been a solid platform of ice, there was suddenly a chaos of icebergs and smaller fragments, a jigsaw puzzle scattered across the dark water. The collapse of Larsen B was the culmination of a longer process. The Antarctic Peninsula had been warming for decades. Air temperatures had risen faster there than in almost any other place on Earth, increasing by nearly 3 degrees Celsius in the latter half of the 20th century. This warming extended the summer melt season, allowed melt ponds to form more extensively, transformed the surface of the ice shelf from permeable snow into impermeable ice. When an especially warm summer arrived in 2001 and 2, it provided the final push. Melt ponds formed extensively. Water filled the crevasses, hydrofracture propagated through the ice, and the shelf, which had been stable for at least 10,000 years, essentially the entire period since the last ice age, broke apart. The consequences were immediate and dramatic. With the ice shelf gone, the glaciers that had been feeding it suddenly lost the buttressing effect that had been restraining them. Like a cork pulled from a bottle, the glaciers accelerated. Some began flowing 2 to 6 times faster than they had before the collapse. They thinned as they stretched. Their fronts retreated, sometimes by tens of kilometers. Ice that had been grounded on bedrock lifted off and became part of the floating mass. And all of this accelerated ice flow meant that more ice was being delivered from the interior of the Antarctic Peninsula to the ocean, contributing to sea level rise. The collapse of Larsen Bay was not an isolated event. The northernmost section of the Larsen Ice Shelf Complex, Larsen A, had disintegrated in January of 1995. Farther south along the peninsula, the Wilkins Ice Shelf broke up in a series of events beginning in February of 2008. Other smaller ice shelves around the peninsula have thinned, retreated, or disappeared entirely. The pattern is clear. As the peninsula warms, ice shelves that had been stable for millennia are reaching critical thresholds and breaking apart. But the Antarctic Peninsula is an outlier. It is warming faster than most of Antarctica. The vast ice shelves of the Ross and Filchner Ronne, far to the south in much colder regions, are not currently threatened by surface melting. Air temperatures there remain well below freezing year-round, and melt ponds do not form. But these shelves face a different threat, one that comes not from above but from below. The ocean is warming. In some regions around Antarctica, warm water from the deep ocean is finding its way onto the continental shelf, reaching the grounding lines of major ice streams and driving rapid basal melting. The most concerning example is the Thwaites Glacier in West Antarctica, sometimes called the Doomsday Glacier, because of its potential to contribute significantly to sea level rise. Thwaites has an ice shelf, but that shelf is thinning and fracturing. Warm ocean water, water that is several degrees above the freezing point, is circulating beneath the shelf and melting it from below at rates of several meters per year. Without the shelf to provide buttressing, Thwaites Glacier could accelerate dramatically, and because it sits on bedrock that slopes downward inland, it could enter a feedback loop where retreat leads to faster flow, which leads to more retreat. Some scientists estimate that the complete collapse of Thwaites and the surrounding glaciers it supports could eventually raise global sea levels by more than 3 meters, about 10 feet. Understanding these processes, predicting how ice shelves will respond to continued warming, determining which shelves are vulnerable, and on what timescale. These are among the most urgent questions in climate science today. The answers matter not just for Antarctica, but for every coastal city on Earth, for the hundreds of millions of people who live within a few meters of sea level, for the infrastructure and agriculture and freshwater supplies that depend on stable coastlines. Studying ice shelves is extraordinarily difficult. They exist in some of the most remote and inhospitable places on the planet. Reaching them requires specialized ships that can navigate through sea ice or aircraft that can land on the ice surface, or both. Once you arrive, the environment is brutally harsh. Temperatures during the Antarctic summer, the only time of year when most research can be conducted, typically range from -10 to -30 degrees Celsius. Winter temperatures can drop below -60. Winds can exceed 100 kilometers per hour. Whiteout conditions, where blowing snow makes it impossible to distinguish ground from sky, can persist for days. Even reaching the ocean beneath an ice shelf is a monumental challenge. The ice is hundreds of meters thick. Drilling through it with conventional mechanical drills is slow, difficult, and limited to relatively thin ice. Instead, scientists have developed hot water drills, systems that can melt a hole through the ice by pumping thousands of liters of hot water down a hose. These drills can bore through several hundred meters of ice in a day or two, creating a cylindrical shaft just wide enough to lower instruments through. Once the hole is made, researchers must work quickly. In the frigid air, the hole can refreeze and close within hours or days. Through these holes, scientists have lowered cameras to film the underside of ice shelves. They've deployed sensors to measure temperature, salinity, and currents. They've collected water samples and sediment cores. They've used nets to capture organisms living in the sub-ice cavity. Each hole provides a tiny window into an otherwise inaccessible world, a single point of observation in a realm that extends for hundreds of thousands of square kilometers. Autonomous underwater vehicles, AUVs, offer another way to explore beneath ice shelves. These robotic submarines can be deployed through a borehole or from the ice edge, then programmed to swim beneath the ice, mapping its underside with sonar, measuring water properties, even filming the seafloor. Some AUVs can operate for days or weeks, covering distances of hundreds of kilometers, providing data from regions that would be completely inaccessible by any other means. But deploying an AUV beneath an ice shelf is risky. If the vehicle malfunctions or gets disoriented, if it runs out of power or becomes trapped in a crevasse, there is no way to retrieve it. It's lost, along with all the data it collected. Satellite observations provide a complementary perspective. Satellites cannot see through ice, cannot directly measure what happens in the sub-ice cavity, but they can track changes at the surface. Radar altimeters measure the height of the ice shelf with centimeter precision, allowing scientists to detect thinning or thickening. Interferometric synthetic aperture radar (INSAR) can measure horizontal motion, tracking how fast the ice shelf flows and identifying areas where cracks are forming or where the shelf is flexing with the tides. Optical satellites capture images that show melt ponds forming on the surface, icebergs carving from the front, and the large-scale breakup of collapsing shelves. By combining all these approaches, by integrating data from satellites, from surface camps, from hot water drill holes, from AUVs, scientists are gradually piecing together an understanding of how ice shelves work. They're measuring the rates of basal melting. They're mapping the circulation of water in the sub-ice cavities. They're identifying the stress fields that control where cracks form. They're quantifying how much ice is being delivered by glaciers and how much is being lost to calving and melting. They're using this information to build computer models that can simulate ice shelf behavior and project how it might change in the future. These models are becoming increasingly sophisticated. They couple the ice dynamics with ocean circulation, representing how melting at the ice base affects the water properties, and how those changed water properties in turn affect melting. They include the effects of tides, which had often been ignored in earlier models but are now recognized as crucial. They represent the structural mechanics of ice, how it fractures and carves, how rifts propagate, how large tabular icebergs eventually break away. Running these models requires supercomputers, massive computational resources, and even then the simulations are limited by uncertainties in the underlying physics and by the lack of detailed observations from many parts of the Antarctic ice sheet. Yet for all the scientific effort, for all the sophisticated technology and complex models, there remains something deeply mysterious and humbling about ice shelves. They exist at a scale that defies human intuition. A single ice shelf can be larger than many countries. The ice is so thick that it takes light more than a microsecond to travel through it. The cavity beneath contains more water than many inland seas. The organisms living there have been growing in darkness for longer than human civilization has existed, and they are not permanent. Ice shelves come and go on geological timescales. They form during cold periods, when glaciers advance and ice accumulates. They collapse during warm periods, when melting exceeds growth. There is evidence that some of the ice shelves currently around Antarctica did not exist during the slightly warmer climate of the early Holocene, the period 6,000 to 8,000 years ago, when temperatures were perhaps a degree or two warmer than the pre-industrial average. There is evidence that during the last interglacial period, about 120,000 years ago, when temperatures were even warmer, many Antarctic ice shelves may have disintegrated entirely. They reformed during the ice age that followed, grew during the cold millennia, and persisted into the modern era. But now, as the planet warms again, as carbon dioxide concentrations rise to levels not seen for millions of years, they are beginning to respond. Some are thinning, some are cracking, some, like Larsen B, have already collapsed. The great question is, what will happen to the large ice shelves, the Ross and the Filchner Rhone, the platforms that buttress massive portions of the East and West Antarctic ice sheets? These shelves are far from any current threat of surface melting. They sit too far south, in regions where temperatures remain well below freezing even during the warmest summers. But the ocean is changing. If warm deep water continues to intrude onto the Antarctic continental shelf, if circulation patterns shift, if the right combination of conditions develops, these shelves could begin to thin significantly from below. Models suggest that the Filchner Rhone might be particularly vulnerable later this century if ocean temperatures continue to rise. Should these great shelves thin substantially or break up, the consequences would be profound. The glaciers they currently buttress would accelerate. Ice flux into the ocean would increase dramatically. Sea level rise would accelerate. The timescales are uncertain. The feedbacks are complex, but the potential is there for substantial changes that would reshape coastlines, that would force the abandonment or expensive protection of major cities, that would alter the course of human history. But we are not there yet. For now, the ice shelves remain. They float in their cold embayments, flexing with the tides, flowing slowly seaward, cracking and carving and reforming. Beneath them, the dark water circulates, carrying its hidden cargo of nutrients and organisms. The ancient communities of sponges and corals and strange patient creatures continue their slow existence, unaware of the debates and projections and concerns of the surface world. The ice records the climate of the past in its layers. The ocean records the changes of the present in its temperature and chemistry. And together, these quiet kingdoms beneath the ice bear witness to a planet in transition. Tonight as you rest, think of those dark waters, those hidden ecosystems, those platforms of ice larger than nations. Think of the slow circulation of water in cavities no human has ever entered. Think of organisms that have been filtering nutrients from passing currents since before the pharaohs ruled Egypt, since before Stonehenge was built, since before agriculture was invented. Think of ice that has been flowing for thousands of years, ice that started as snow falling in the interior of Antarctica before cities existed, before writing was invented, before our species had spread across the globe. There is something profoundly peaceful about these timescales, about these slow processes unfolding over millennia. In our daily lives, we operate on timescales of seconds and minutes and hours. We worry about tomorrow, plan for next week, think ahead to next year. But ice shelves remind us that the Earth operates on timescales that dwarf our personal experience, that the planet has a memory measured in millennia, that changes we make now will echo through time in ways we can barely comprehend. The ice shelves are, in their own way, archives of climate. Their thickness, their extent, their stability, all depend on the delicate balance between accumulation and loss, between the cold of the atmosphere and the warmth of the ocean. They are sensitive indicators, responding to changes that might be subtle or gradual, but that accumulate over time. They are canaries in the coal mine, early warning systems that can tell us when the balance is shifting, when thresholds are being approached. And they are, perhaps more than almost anything else in nature, humbling. They remind us of our place in the vastness of geological time and planetary systems. In the darkness beneath an Antarctic ice shelf, a sponge that sprouted from a lava 5,000 years ago continues to filter water. Currents flow past it, carrying nutrients from distant seas. The ice above flexes with the tide, rises and falls, a rhythm that has continued for as long as the sponge has lived. The sponge does not know about climate change. It does not know about the debates and models and projections. It simply exists, growing atom by atom, filtering microbe by microbe, a small living thing in a vast dark space, patient and persistent and quietly alive. Somewhere on the Ross ice shelf, snow is falling. Each flake settles on the surface, adds its tiny weight to the burden pressing down. Over the years, those flakes will be buried by other flakes. They will be compressed. The air between them will be squeezed out. They will become ice, will begin the long, slow journey toward the sea. Hundreds of years from now, thousands of years from now, that ice will reach the ice front. It will crack away as part of a giant tabular iceberg. It will drift north into warmer waters, and it will melt, releasing the water molecules that fell as snow all those centuries before, returning them to the ocean, completing the cycle. The ocean continues its circulation. Cold water sinks in polar regions, carrying oxygen and nutrients into the depths. Warm water rises in the tropics, carrying heat toward the poles. The great conveyor belt of ocean circulation, driven by differences in temperature and salinity, moves water around the planet, connecting all the oceans, linking surface and deep, equator and pole. The ice shelves are part of this system. The meltwater they produce, cold and fresh, contributes to the formation of Antarctic bottom water, the densest water in the ocean, water that sinks to the abyssal depths and spreads throughout the world's oceans. In this way, the ice shelves help drive global circulation. They are not isolated features, but integral parts of the planetary climate system. And so we return to where we began, to the idea of floating platforms of ice, vast beyond comprehension, drifting upon dark seas, to hidden cavities filled with ancient water, to life persisting in darkness, to slow changes unfolding over timescales that span empires and civilizations. The ice shelves are quiet kingdoms, realms of cold and darkness and patient life. They are among the last truly wild places on Earth, environments where human influence is only now beginning to be felt, where nature still operates according to its own logic and its own timescales. As you drift towards sleep, let these images settle in your mind. The vast white expanse of an ice shelf stretching to the horizon. The dark water flowing beneath, stirred by tides and currents, the ancient sponges anchored to boulders in absolute darkness, the slow forward creep of ice toward the sea, the crack and groan of bergs calving, the flutter of an icefish's fins in water just above freezing, the patient growth of marine ice crystals on the underside of the shelf, all of it happening in silence, in cold, in the stillness of polar night that lasts for months. You are connected to these places, as distant and alien as they seem. The water that falls as snow on the Antarctic ice sheet is part of the same hydrological cycle that brings rain to your home. The ocean that circulates beneath the ice shelves is the same ocean that washes your shores. The climate that shapes these frozen platforms is the same climate that determines your weather. We are all part of one system, one planet, one interconnected web of atmosphere and ocean and ice and life. And tonight, the ice shelves continue their ancient existence. They float upon the southern seas. They harbor their hidden ecosystems. They record the passage of time in their layers. They flex with the tides and flow with the glaciers, and slowly, slowly change. They are not eternal. Nothing is, but for now they remain. Vast and cold and patient, quiet kingdoms beneath the ice, waiting for whatever the future brings, indifferent to our concerns, magnificent in their utter alienness, beautiful in their stillness. Rest now. Let your breath slow. Let your muscles relax. Let your mind settle into the gentle rhythms of the deep, like water flowing beneath ice, like snow accumulating in layers, like ancient sponges filtering nutrients. Find your own slow pace. Find your own stillness. The world will continue its turning. The ice will continue its flowing. The ocean will continue its circulation, and you can simply rest here in this moment, held safely in the present, surrounded by the quiet vastness of a planet that has existed for billions of years and will continue for billions more. The ice shelves are still there, floating in the darkness at the bottom of the world. And you are here, warm and safe, drifting gently towards sleep. Let the images fade. Let the facts and numbers blur. Let only the sense remain. The feeling of vastness and coldness and deep time. The ancient water, the floating ice, the dark spaces between, and sleep. Slowly, peacefully, into the quiet night. If you happen to still be awake, you can go ahead and watch the next chapter now. Sleep well and dream softly. Good night.